Okay, so golf balls must meet a set of 5 standards in order to be used in professional tournaments. One of these standards is distance traveled. When a ball is hit by a mechanical device, the iron barren with a 10-degree angle of launch, a backspin of 42 revolutions per second, and a ball velocity of 235 per second. The distance the ball traveled may not exceed 291.2 yards. Manufacturers want to develop a ball that will be as close to 291.2 as possible without exceeding that distance. A particular manufacturer has determined that the distance traveled for the balls it produces are normally distributed. That's important because as soon as we say that, oh, we can use the normal, with a standard deviation of 2.8 yards. This manufacturer has a new process that allows it to set the mean distance the ball will travel. All right, so they're telling us it'll set the mean. And if the manufacturer sets the mean distance traveled to be equal to 288 yards, what is the probability that a randomly selected that a ball that is randomly selected will travel too far? So when I look at that, it's like, okay, what have they told me? Well, they've told me it was normal. And they told me they set the mean at 288. And we're looking for the probability that a single ball traveled too far. So Z equals X minus mu over sigma. So the probability that Z, and we shade it to the right, so greater than 291.2 minus our mean of 288 all over our standard deviation of 2.8. Now I have a couple ways to run this through the calculator. I can use the second vars, or I can go ahead and use the stat test. So stat, you know what, I want to switch calculators, so bear with me a moment. Hopefully this one will show up a little better than that one. Yeah, I think so. So stat, arrow over to word test, and I'm going to use a z-test, and my mean in this case was 288. The standard deviation was 2.8. We're not working with an X bar, we're working with an X because we're working with a single value, so 291.2. And our sample size, we're looking for a randomly selected ball, so 1, and we shade it up and to the right. When I calculate that, I end up getting the z-score, and it's really important that you get that z-score. So that yields the probability that Z is greater than 1.1428, and we need to give the z-score, which equals 0.1265. All right, so there's about a 12.5% chance that the ball will travel too far, and we probably should write a little sentence saying that there's a 12.5% or 12.65% chance that the ball will travel too far. Part B, what is the probability that the first ball that travels too far is the 6th ball tested? All right, what's the probability that the first ball that travels too far is the 6th ball tested? So in this case, that means we have this 1, 2, 3, 4, 5, 6. This one travels too far. These do not travel too far. All right, so these don't travel too far. And so how am I going to do that? Well, those are going to be equal to 1 minus the 0.1265. And I can raise that to the 1, 2, 3, 4, 5th power. And this is going to be 0.1265 to the 1st power, because this is a geometric, and it's going to be a geometric PDF. So on the calculator, that's the way I'm going to work this. And by the way, this will qualify for my work shown. On my calculator, I'm going to go second vars, geometric, PDF. My probability that travels too far is 0.1265. And is specifically on the X value, or the 6th one. So in this case, I end up getting a value of about 0.0643. So there's about a a 6.4% chance that the sixth ball tested will be the first one to travel too far. Now, the next thing is, what is the probability the first ball tested that travels too far is among the first 5 balls? So at this point, once again, we have the keyword first. So this lets me know it could be it's a geometric, but it could either be the first ball, the second ball, the third ball, the fourth ball, or the fifth ball. And since it can be multiple values, this makes it a CDF. That's different than this one, where we had 1, 2, 3, 4, 5, 6, 7, 8, and it could only be a singular value. So this one was a geometric PDF. This is going to be a geometric CDF. All right. Now, I need to show my work. So my work in this one is going to be, well, what's the probability that happens on the first one? The probability that happens on the first one is just 0.1265. And then we need to know the probability that it happens on the fifth one. So plus dot, 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 plus. And I'm going to have 1 minus 0.1265. And then the 0.1265. And this will always be to the first power. And 5 minus 1 gives me 4, so this is to the fourth power. And that would qualify for work shown. So this is a geometric CDF, and we'll use our X value will be 5. So when I do that, I'm going to go, once again, second vars, geometric CDF, 0.1265, and our X value being 5. And I end up getting a value of about 0.4914. I'm going to pause this for just a moment. Okay, so I got 0.4914. So that's the probability that it happens among the first 5 shots. Now, please remember the first 5 balls. That means it could be either the first one, the second one, the third one, the fourth one, or the fifth one. It could be any one of those. And really, remember that a CDF is just the sum of the individual PDFs. So it's the PDF of 1 plus the PDF of 2 plus the PDF of 3 plus the PDF of 4 plus the PDF of 5. Okay? So the next one, if the manufacturer tests 5 randomly selected balls, so now we're testing a specific number. What is the probability the mean distance exceeds the maximum distance of 291? So they're asking us about the mean. So that means they're asking me about X bar. So that clues me in that I'm using this formula, Z equals X bar minus mu sigma divided by the square root of N. So we swap formulas. Now we're still working with a normal. And we know that they told us earlier that the mean was 288. We had a standard deviation of 2.8. But now we're talking about, we want to know whether it travels more than 191.2. So essentially the same problem, but we want to know whether or not the X bar or the average, in other words, whether 5 of them travel too far. So this is going to look like this. The probability that Z is greater than 291.2, that average, minus the 288 over the standard deviation of 2.8 divided by the square root of, in our case, our N happened to be 5, our sample size is 5. So this would be our work shown. All right. So I can do this again very nicely if I go to stats test Z test. So let's do that. We'll go to stats test Z test, stats test Z test, press enter. My mean is still 288. My standard deviation is 291.2, but now I've changed my sample size to 5. I still need to be a greater than because we shaded up and to the right. And I end up getting yields the probability that Z is greater than 2.555, and that equals 0.0053. So in other words, Pretty small chance of that happening. And yes, you could have used the normal CDF, but this part will give me the z-score, which I have to have. All right. So part E, assume that the mean distance traveled is 2.88 and that the 5 balls are independently tested. What's the probability that at least one of the 5 balls, excuse me for just a moment, I need to pause this. Okay, so assume the mean distance traveled is 288 and the balls are independently tested. What's the probability that at least one of the 5 balls will exceed the maximum distance? Well, we know we have a specific number, which is 5 balls, okay? So we want to know, gosh, what's the probability that one will exceed the maximum distance? Or at least one. Well, whenever I see that at least, I know I'm doing a 1 minus. And in this case, I have a specific number. And because I have a specific number, I know that we're talking about a binomial. So we have 0, 1, 2, 3, 4, 5, 6, ... to infinity. But at least one of the 5 means it could be the first one, the second one, the third one, the fourth one, or the fifth one. This really doesn't go to infinity because we have exactly 5 balls. So I want to do 1 minus the probability of 0. All right. So 1 minus the probability of 0. And so we're going to start off and go, well, you know what? Specific number, that makes it a binomial because we have a specific number of trials. So I need to show the sum of the PDFs, which should be the PDF of 1 plus PDF of 2 all the way to PDF of 5. So I go 5, choose 0. And I go, ooh, I need the probability. What's the probability that 1 ball travels too far? Probability that 1 ball travels too far is 0.1265. So we're going 5, choose 0. The probability that a single ball travels too far is 0.1265. That came from part A that we previously calculated. When we did this, we said, oh, the probability that 1 travels is this much. So this is the probability, and this is going to be to the 0 power. And this is going to be 1 minus 0.1265 to the 5th power plus ... plus 5, choose 5, excuse me. And by the way, I need to change this. This needs to be the 1st power because we're doing the PDF of what we want. So 5 to the 1st. So this needs to be the 1. And this needs to be the 4th. I apologize for that. Here's why. Once again, we want 1, 2, 3, 4, and 5. So 5, choose 1, 0.1265 to the 1st. 1 minus that to the 4th, plus 5, choose 5, 0.1265 to the 5th, and 1 minus 0.1265 to the 0 power. So that qualifies for work shown. But what am I going to do in the calculator? In the calculator, I'm going to do a 1 minus the binom CDF of 0, because we're going to always subtract out the highest thing we don't want. We want 1, we want 2, we want 3, we want 4, we want 5. We don't want 0, so we're going to subtract out 0. So in this case, 1 minus second vars binomial CDF. Trials happen to be 5. Our probability was 0.1265, which we got from part A, and we're going to have 5 balls, so this will be 5. And oops. So I did something incorrect. 1 minus second vars binomial I'm sorry, my X value is 0 because that's what we're subtracting out. We're subtracting out the highest thing we don't want, which is 0. And we end up getting 0.4914. All right. So about 0.4914. All right. The last one. If the manufacturer wants to be 99% certain, so this is interesting, they give me an area. And if they give me an area, good chance that this is going to be an inverse norm because they gave me a percent or an area. So If the manufacturer wants to be 99% certain that a randomly selected ball will not exceed the maximum distance of 299, what is the largest mean that could be used in the manufacturing? Let's draw a picture. And we want to be 99% sure that the ball does not exceed 291.2. So if I have to do that, I'm going to need to draw a picture and go, gosh, what's my mean? Well, obviously, my 291.2 is going to be down here. And when I do that, hold on for just a second. I need to reread that question. It says will not exceed. So we have to be below that. So this area needs to be 0.99, and we need to be 291.2. But we're looking for the mean. We don't know what the mean is in this case because they want us to find what is the largest mean that can be used in the manufacturing process. So I go to my z equals x minus mu over sigma, and I start plugging in what I know. Well, I know I don't have my mean. I can't exceed this 291.2. That I can't exceed. And I know my standard deviation is 2.8. Well, I have a problem here. I don't have my mean and I don't have a z-score. But because I have the 99%, I can go ahead and calculate that z-score by going second vars, inverse norm, which is 0.99, mean is 0, standard deviation of 1, and I end up getting a z-score of 2.326. Now I can solve that by algebra, and this, by the way, having that z-score is really important. I can solve this by algebra, which is what I'll have to do at this point. So I'm going to go, this should be a positive 2.326. So my 2.326 times the 2.8, which was right here. Then I'm going to subtract minus 291.2, and I end up with a negative 284.68, but that equals a negative mean. So basically my mean needs to equal 284.68. That's the maximum value. So 284.68 is the maximum value that this mean can be. So let's try that out. Let's check that out, because we can check that with the norm CDF, second vars, norm CDF, lower bound, negative infinity, upper bound, 291.2, we can't exceed that. Mean happens to be 284.68, and our standard deviation is 2.8. And sure enough, I get about 99%. I'm going to do that one more time. Second vars, normal CDF, lower bound, negative infinity, upper bound, 291.2, because I can't exceed that. My mean of 284.68 and standard deviation of 2.8. And I get about 99. All right, thank you.